Let's do one more example where we calculate the derivative using the definition before we move into the topic for today. And then I will make a comment about something that we can use in today's video and the next one. So we will find the derivative of x cubed using the definition, which I have written here. It's a limit h approaches 0, f of x plus h minus f of x divided by h. And if you have seen the last video, for example, you know I will typically begin with the numerator here and simplify. My goal is to get this quantity as h times something. Here we go. This is x plus h cubed minus x cubed. Now this is going to be some algebra, but it is not too terribly bad. It's a little bit more involved than when we did f of x is x squared. First, I will multiply these two. I get x squared, I get 2xh and h squared, and then I will multiply this one and this one. X cubed plus 2x squared h plus xh squared, and then plus hx squared plus 2x h squared, and then plus h cubed minus x cubed. Now I can simplify this a little bit. The only thing that adds to 0 is x cubed minus x cubed, but I can combine. Let's see. These two match. They have an xh squared. Don't add to 0, but they match. And similarly, here I have x squared h, x squared h. These two match. So what's underlined in red, maybe with two underlines so you can see it better, those add to 0, and then the others are just like terms. So what do we get here? We have 3x squared h plus 3xh squared plus h cubed, which is h, times 3x squared plus 3xh plus h squared. Now let's divide by h. This seems like a lot of x's and h's, but we're exactly where we need to be. F of x plus h minus f of x divided by h is 3x squared plus 3xh plus h squared. Now the derivative is a limit as h approaches 0 of this, which we can substitute h equals 0. This term is 0, this term is 0, we get 3x squared. Okay? So what we can do from this is you can sort of add. Now we know how to differentiate x cubed. We can add that into our catalog of functions that we have. Let me move out of the way, but that we have actually calculated the derivative for. The derivative of x cubed is 3x squared. These are all derivatives we have seen either in the last video or here, x cubed we just calculated. Now, there is a general rule here, okay, which I will mention now, and you can use in this lesson and the next lesson. Then we will move into lots of rules for derivatives, and I will mention it again. But if you know the rule now that you are sort of seeing, it can help you when it doesn't specifically mention you must use the definition of derivative, okay? Because what we're going to discuss today is extrema, local max, local min, intervals of increasing and decreasing, and knowing this power rule that I will mention can help you So you don't have to use the definition every time. Okay, so the general rule here, which we may use, is called the power rule. It says the following: you take the derivative of x to the n. This is nx to the n minus 1. Here, n is any number. Okay, it can be fraction, decimal, positive, negative, 0, any number. This works. And the way I remember it is I always tell myself, bring down the power, x to the power minus 1. This is the power rule, and we see it here, right? This is x to the 1, so we would bring down the power, x to the 0. We know x to the 0 is 1, okay, so this fits here. X squared would be bring down the power, x to the power minus 1, okay? This works too. X cubed, bring down the 3, x to the 3 minus 1 is 2. It looks good, right? Now this one, well, we did this using the definition, but what power is this? This is x to the 1/2, and by the power rule, this says bring down the power, x to the power minus 1. And you see this, if you rewrite it, is exactly 1/2 square root of x. So this also power rule. Now even this, technically, the derivative of a constant being 0, you could write, well, maybe I'll change this slightly just to say the derivative of 1 is 0, and then we could use our other property we mentioned that would work for any constant. But how could you interpret this using the power rule? Well, 1 you may write as x to the 0, and then bring down the 0, x to the, you see, technically 0 times anything is 0. You could also think about the derivative of a constant as coming from the power rule as well, okay? So this is something you can use when you're doing intervals of increasing or decreasing, local max and min, absolute max and min. All of these we will discuss today. You can use the power rule unless you are asked to use the definition of derivative. Now for the topic of today, which is extrema. Here I have graphed a function, f of x. This is continuous, we can see. And I have 1, 2, 3 points marked as sort of special points on this graph. The first thing you will notice is the highest y value attained by this function is y equals 5, and this is one type of extreme value. But I want to make a different comment first. So let's stand, well, okay, we can stand here or we can stand here. Maybe let's stand at this point, 7/2, comma 4. Okay, here we are. If you look on each side of that point on the graph, the function values are less than or equal to 7/2, right? Look this way, look this way. The function values, well, in this case, they're less than 7/2, but they are lower, okay? This means that this point at x equals 7/2, which is here, we have what's called a local maximum. So we have a local maximum of y equals 4 at x equals 7/2. And I started with this one just to point out this is a local max, even though clearly 4 is less than 5, right? To be a local max, it doesn't mean that you're the highest y value, just right around that point. It's the highest y value that you see. Okay, we see that here. Now, of course, this point, which is the highest overall y value, y equals 5, this is also a local max. Because if you stand here at the point, now I'm blocking it. If you stand here at 0, 5, you look on either side, the function value is less. So we also have a local max of y equals 5 and it occurs at x equals 0. Okay, now these are the only two local maxima in the picture, but this point 2, 3 is another special point. If you stand at the point 2, 3, this, okay, now you have to look up in both directions. The function value on either side is greater than y equals 3. Look this way, look this way. This is a local minimum. So we have a local minimum of y equals 3 at x equals 2. Now, great, wonderful. We have the concept of local minimum, local maximum, or generally, if you're either minimum or maximum, it's a local extremum. That's this, extrema. Okay, but there are a few things I need to point out here. And one of them is this other concept of global. So we only have one global max. You will also see absolute maximum for a global, and this is y equals 5 at x equals 0, and we have no global minimum. Well, the limit as x goes to infinity of f of x is minus infinity. And similarly, maybe I'll write that here in a bracket, the limit as x goes to infinity of f of x is negative infinity. And similarly, the limit as x goes to minus infinity of f of x is minus infinity, just looking at the graph. But this was kind of a side comment. We have no global minimum while this function is unbounded below. And so there is no lowest overall y value. Okay, now let's get into a definition. So maybe I'll put this in a box, which comes into play here. Definition, a point x in the domain of a function f of x is called a critical point provided, well, two things. So I am defining critical point, and an x value is a critical point provided either the derivative is 0 at x or the derivative is undefined. So either f prime of x equals 0 or f prime of x does not exist. Okay, this is a critical point. Well, let's think about this right now. In this picture, I have 3 critical points. This one, x equals 2, is a critical point. Why is that? Well, this is a cusp right here at 2. F prime of 2 does not exist. Okay, x equals 2 is a critical point. And then this part, f prime of x equals 0, it says that the slope of the tangent line is 0, or equivalently, you have a horizontal tangent line. So you see at this point, horizontal tangent line, m equals 0, and at this point, horizontal tangent line, m equals 0, okay? So my 3 critical points for this function are exactly these three special points I started off with. X equals 0, x equals 2, x equals 7/2. Okay? Perhaps one more definition, and that is a critical value is the y value at a critical point. Okay, so x values can be critical points. They're points in the domain where the derivative is 0 or does not exist. And then when you have a critical point, the corresponding y value is a critical value. Okay, so 4 is a critical value corresponding to critical point 7/2. 5 is a critical value corresponding to critical point 0, and 3 is a critical value corresponding to critical point 2. Okay, now what we were noticing in this picture about these 1, 2, 3 critical points, these are exactly the points where we have a local max and a local min. I erased to give myself a little bit more space to state this theorem because it's quite important. So let me state that here. And it says the following. If f of x has a, maybe I'll say a local extreme point at x, or maybe I'll say at x equals c, so at some specific x value, we have a local extreme point, then x equals c is a critical point for the function. What this says is that if f has a local extreme point, meaning local max or local min, and we see 3 of them here, local max, local min, local max. Okay, so if you are in this situation, then the x value is a critical point, meaning, well, it's erased here, but meaning either f prime of x is 0 or f prime of x does not exist. And we see that here. Derivative is 0, derivative is 0, the derivative does not exist. Okay? Now, let me make a few notes here before we move on. The first one goes back to, well, what I had here, which is the concept of a global max and global min. So if a function has a global max or min, maybe I will just say extremum, at x equals c, then f of x has a local extreme value at x equals c. Okay? This makes sense if you are the highest overall y value at some x equals c. Well, certainly, right around yourself, you can look and the function is less than or equal to right around yourself, okay? Or similarly, if you are the lowest overall y value, that would say global minimum. Then you look up in each direction, the function value will be greater or greater than or equal to, okay? So certainly this is the case. And then the second note that I will make is as follows: just because some function has a critical point at x equals c does not guarantee f of x has an extreme point either local or global, at x equals c, okay? This statement, the note number 2, is very similar to this theorem, except it says it does not go in the other direction. So if you have a local extreme point, then you have a critical point at x equals c, but it does not go the other way. You can have critical points where the function does not have a local max or local min at that x value. And perhaps let's see a quick example of a function like this right now. If we look at f of x is x cubed, well, we just calculated the derivative of this using the definition. It was 3x squared, although we could also use power rule in this section. But where is, well, first of all, the derivative exists everywhere, and it's 0 only when x equals 0. Okay, so x equals 0 here, this is our critical point. But let's look at the graph, which more or less, this is the shape of x cubed. Is 0 a local max or a local min? No, right? If you stand here at 0 and you look this way, there are y values less than you. If you look this way, there are y values greater than you. So you are not a local max or local min. So 0 here is a place where we in fact have a horizontal tangent line, but it's not a local max or local min. Okay? Maybe my third note, if I could have kept writing below, I would have. My third note is if you take the domain to be a closed interval, a to b, then x equals a and b are both critical points. So make sure, if you, for example, have a question, here's f of x, and here's a closed interval to work with, find the critical points, a very natural question to ask. Make sure you include the endpoints. And really the reason here is that the derivative is undefined at the endpoints, technically, okay? Here's an example of using a closed interval. So I'm looking at x squared, but I'm not looking at x squared on its natural domain of all real numbers. I'm looking at it on this restricted domain of this closed interval, -2 to 3, and I have it graphed here. So this part of the graph of x squared is my whole function. Okay, I'm only looking at this on the closed interval. So let's find critical points, and then we will look at extrema. The derivative we know is 2x. Now technically that's the derivative just on the open interval, because I just mentioned that the derivative is really not defined at the endpoints. But in any case, the only time this is 0 is at 0. So 0 as 2x means that x equals 0. So now I can write a list with my critical points. My critical points, we have 0, we have the 2 endpoints. Now, immediately, local max, local min, let's look at those. This I'm going to do by looking at the graph for this example. We see a local min. So we have a local min, mum of y equals 0, and it occurs at x equals 0. We have a local max. Well, we have 2 local maximums. here 9, and this occurs at x equals 3, and then here is another local max. We have another local max of y equals 4. It occurs at x equals minus 2. Now, you might think, why is, for example, this a local max? You must remember, we're only looking on minus 2 to 3. This is our whole world, right? So you're standing here at minus 2 comma 4, and all you see is function values less than, right here, less than. This part, which is part of x squared, is, if you think about it, on the whole real line, but not on just this closed interval where we only see values less than, like this. In this example, we have both global max and global min. So which one? Let's see. This is a global min. So this one here is also global. And this one here is global max, because it's the highest overall y value. Right here it is. There's no y value higher than that for f of x is x squared on closed minus 2 to 3. Okay? And this is not by chance here. Every time you have a continuous function on a closed interval, you will have both a global max and a global min. So this is called the extreme value theorem. I'll write it as a fact. If f is continuous on the closed interval a to b, then f attains a global max and global min on this interval. Okay, this is why we love closed intervals, because every continuous function on a closed interval attains both a global max and a global min. I have returned to this original graph to address the following question, and that is, how can we determine if critical points correspond to local maxima, local minima, or neither? So far we have looked at graphs and what does it look like, okay? But the answer to this question, let's say in the absence of a graph, how would you? Well, of course, calculus, but let's get a little bit more specific, okay? So the answer here is we will use intervals of increasing and decreasing. Now, let me define both of these concepts, because this is important definition. So let's say, given a function and an interval. So a function, f of x, is increasing on an interval I, provided f of a is less than f of b whenever a is less than b on I. Okay? Now, technically, I will just say this, your book calls this strictly increasing, okay? And for just increasing, they put a equals here and it equals here, and other texts call that non-decreasing, but it's fine. I'm going to refer to this concept as increasing. And then a function, same idea, but I will define decreasing. Decreasing on an interval I, provided f of A is bigger than f of B whenever A is less than B on I. Now, I think I have enough space here to go back to this graph and write down the open intervals of increasing and decreasing. Maybe I will do this in blue. So for this function, okay, f of x is increasing on and then decreasing on. Okay. So let's look at the picture and then we will talk about the calculus side of increasing and decreasing. Well, first of all, we read functions left to right, just like you read words on a page. Okay, so you start coming in this way. The function, look, here we are increasing up to 0. So minus infinity to 0. Okay, and then starting at 0, we decrease to 2. And then from 2 to 7/2, increasing. And then finally 7/2 to infinity, decreasing. Okay, so we have listed, just looking at the graph, the open intervals where this function is increasing and decreasing. And what you see here is that these intervals are definitely related to where we have local max and min, because here we have a local max, we are increasing up to that local max, and then we are decreasing after. We are decreasing to here, and then we are increasing after. We are increasing to this point, and then we are decreasing after, right? So the relationship we definitely see without even writing down derivatives or anything like that yet. We definitely see there's a relationship between intervals of increasing and decreasing and local max and local min, okay? So now let's get into the calculus part of the answer to this question. Suppose f of x is differentiable on an open interval. So now I is an open interval, just like we saw down here for my intervals of increasing and decreasing, okay? Suppose f of x is differentiable on an open interval I. Then, okay, now there's two parts to this. Part one is if the derivative is positive on I, then the function is increasing on I. And the second part, if the derivative is negative on I, then the function is decreasing on I. Okay, that marker is dying. But, okay, this is very important. If the derivative is positive on an open interval, that's instantaneous rate of change is positive on an open interval, then the function is increasing. If the derivative is negative on an open interval, okay, instantaneous rate of change is negative, then the function is decreasing. Now, how are we going to use this? Well, we can use the derivative to find open intervals of increasing and decreasing, and then based on that, we will classify critical points as corresponding to local max and local min. Now, let me just say, what does this come from? It comes from something called the mean value theorem, and I'm going to get to that at the end of the video today. Okay, so for now, you can just take this as a fact, and then we will discuss where it comes from later in the video. Here's a function. F of x is 4x cubed minus 9x squared minus 30x plus 6. We will find critical points. We will find open intervals where the function is increasing, open intervals where the function is decreasing, and then I will also, even though I don't have it written, I will also address the question of local max, local min, using this information. Okay, well, let's get started here. The first thing that we need to find critical points is we need to calculate the derivative. And here is where we can use the power rule. So for part A, the first thing we do, this would be 4 times the derivative of x cubed, and then minus 9 times the derivative of x squared minus 30 times the derivative of x, and then the derivative of a constant is 0. This becomes 12x squared minus 18x minus 30. We set the derivative to 0. Well, first of all, this derivative is defined on the whole real line, okay? So we set the derivative to 0. And what can I factor out of all three terms? 3. Oh, no, I can factor out a 6. Okay, factor out as much as possible. It will help you. At least this is my strategy. Okay, because here I'm going to factor this. Now, you could use quadratic formula on this quadratic, but I tend to factor things if I can. So I have 6 times, well, it's going to be 2x and x. And then, well, okay, I'm going to have a 5 and a 1, and 1 comes with a minus sign. So I could just try things. I'm going to try 5 and 1 like this because I realize I need to make 3. Will be, if I did a minus here, it'd be minus 5 plus 2. That looks good. Now I have minus 5x plus 2x gives me minus 3x. I multiply these two, I have minus 5. So it seems I have factored correctly. Well, this is 0 provided 2x minus 5 is 0 or x plus 1 is 0. This one gives us x's 5/2. And this one gives us x's minus 1. This is the end of part A. Okay, we have found critical points. There's 2 of them, 5/2 and -1. So what we want to do here is to figure out open intervals of increasing, decreasing. We have the critical points. These are where the derivative is 0, or we could have derivative does not exist, but that doesn't happen in this example. So I will draw the domain. In this case, the domain is minus infinity to infinity. Then I divide the domain into intervals based on my critical points. Open intervals. Okay, what are my open intervals here? This one goes minus infinity to -1, open. Okay, this one, -1 to 5/2, open on each side, right? And then the final open interval is here. Okay, so I've divided my domain into intervals based on the critical points. Now, what I need to figure out is on this open interval, is the derivative positive or negative? Because if we have positive, we can say increasing. And if we have negative, we say decreasing for the original f of x. So how can we do this? Well, you see I have the derivative factored. What I will typically do is make a little chart where we have x, and then the derivative is 6 2x minus 5 x plus 1. And then we can pick a point in each interval and just test. So for instance, and pick something easy. I'd pick an integer. The easiest thing in this interval is I can test x equals 0. In this interval, I could test x equals 3. And in this interval, I can test x equals -2, right? So, and make sure when you're testing the derivative, maybe I'll put that here. When you're testing the derivative, make sure you actually get a number in the open interval. I see people mess up. Now, what matters here is the sign SIGN, because if I get positive derivative, as I have said, the function is increasing. If I get negative derivative, the function is decreasing. So the actual value of the derivative doesn't really matter. That's why you can pick any point in the interval. What matters is the sign, SIGN. Okay, so let's go here. If I put in -2 to this, well, 6 is always positive. Okay, fine. Here, -2, this would be negative. -2 would be negative, right? So this would be positive. I'm just looking at signs. An even number of negatives multiplied gives me a positive number. An odd number of negatives multiplied gives me a negative number. Put in 0. This is -5, -1, positive. This is negative. Put in 3. This is 6 minus 5, positive. 4, positive, positive. So the sign of the first derivative I will put underneath the interval. Here I had plus, here I had minus, here I had plus. Immediately I can write my intervals of increasing, decreasing. The intervals of increasing, so the function is increasing. Everywhere you see a plus, it's here, this open interval, and this open interval. The function is decreasing. Everywhere we see a minus, which is only one open interval. Okay? So far, we have finished the problem as written, but now let's talk about classifying these two critical points as either being a local max or a local min. I have erased part of the board. We still see this work about the intervals of increasing and decreasing. But how can we figure out? Okay, this is technically something called the first derivative test, but I don't memorize the test. What I do is think about increasing and decreasing. So let me use this information and just sketch, for instance, at -1. We found on this side of -1, the derivative is positive. Maybe I'll write it underneath. And on this side of -1, the derivative is negative. So draw yourself a picture of what this looks like. A sketch, and this is enough to get the idea. Well, this says that we are increasing, and then, okay, horizontal tangent, and then we are decreasing. Well, what kind of extreme point is this? Well, we stand right here and we look each way. The function value is less. This is a local max. So we see we have a local max at x equals -1. Okay, now let's do the exact same thing for the other critical point. 5/2, and we found it's minus and plus. You see I'm using the intervals of increasing, decreasing here. Well, what this says first the function is decreasing, horizontal tangent, increasing. Okay, here's the point. and stare at this picture. What kind of local extreme point is this? Okay, right here, you look on each side, the function is greater. This is a local min. So we have a local min at x equals 5/2. And this is precisely how we can use intervals of increasing and decreasing to classify critical points as corresponding to local max or local min. Okay? This example is a little bit different. We are starting with the derivative. I have it starred in blue. This is the derivative. And then we want to find the open intervals of increasing and decreasing for the original function. This is a very nice problem. How are we going to do this? Well, the first step, we want to find critical points. We know this is where the derivative is 0 or does not exist. Okay? Well, look at the derivative. This is defined on the whole real line. Okay? I can only assume that the function is defined on the whole real line, right? So the natural domain here is all real numbers. And I want to, here, set the derivative to 0. And I can do a little bit more here. This is x plus 3, x minus 3, and then cubed. Okay? Well, we see here, we get x is 0, 3, and minus 3. Okay, now we're going to do the exact same thing we did in the last problem where we make a little chart. I have x, this, okay, I'll write it this way maybe. I'll leave it as x squared minus 9 cubed. And then I need to, forgot my number line. My critical points are here, here, and here, okay? And immediately I can write down my open intervals. We divide the domain into intervals based on the critical points. So here they are, like this. And let's see, I will test. Here, I will use x is -4. Here, x is -1. Here, maybe x is 1, and then x is 4. I didn't have to use those exact values. I could have done -100 and 52, or I could have used -2 and 1. It doesn't really matter, okay? As long as you pick an x value in the open interval. And then this is negative, and this is positive. So overall, I forgot my column for the derivative, we get negative. Okay, at -1, this is negative, but this is negative, positive. At 1, this is positive. This one is negative, negative, and at 4, this is positive, positive, multiply, positive. So what you see here is it goes like this, minus, plus, minus, plus. Okay, this is the sign of the derivative. Immediately, I know the answer to my question. This function is increasing. Now, this is the original function, right? The original function. You use the derivative to answer this question. So my original function, f of x, is increasing everywhere I see a plus, and it's decreasing everywhere I see a minus, like this. Now let's discuss the mean value theorem, which is an important theorem in the theoretical framework of calculus. So our hypotheses are this. f is continuous on a closed interval and differentiable on an open interval. And it says the following: then there exists a c in the open interval such that the derivative evaluated at c is f of b minus f of a divided by b minus a. Now, why is this so wonderful? Well, let's think. What is this? This side, it's the instantaneous rate of change for the function at x equals c. And this side, this is the average rate of change on the interval. This is the average rate of change for the function on the closed interval. Or maybe I should have used this capital I, capital R-O-C, and A-R-O-C just to save writing, but in any case, this is super cool because it says that anytime you're continuous on the closed interval, differentiable on the open, that there is some number in the open interval such that the average rate of change on the interval is the instantaneous rate of change at that x value. Okay, now let's go back to our example where we had x squared on the interval -2 to 3. The average rate of change on -2 to 3 is f of 3 minus f of -2 over 3 minus -2. This was, well, we just square 9 minus 4, over 5. The average rate of change on the interval is 1. Well, we can actually, in this example, we can find it, right? Because what is the derivative? So we know the derivative is 2x. The mean value theorem, it says there is a c. There is c in the open interval with 2c is 1. Well, of course, we can find it here. C is a half. But now let's look at a graph to understand instantaneous rate of change and average rate of change in this example. Well, here's a graph again of this function. F of x is x squared from -2 to 3, and we know the average rate of change is the slope of this secant line connecting these 2 points. This slope is 1, and so it says there is some c here where the tangent line has slope 1, and we calculated it. It's right here at a half, and so this slope of this line, will also be 1, okay? This is what the mean value theorem gives us. We had this on the board, and it was quite important, or one of the most important parts of today, which is the derivative is positive on an open interval. It means the function is increasing on the open interval, and similarly, if the derivative is negative, then the function is decreasing, okay? And I mentioned it came from the mean value theorem. So let's understand this now. Maybe I will just work on one of them. So I will just talk about the reason for number 1, although number 2 is very similar. Okay. So what am I going to assume here? I'm assuming f is differentiable on I. I'm assuming the derivative is positive on I, and I want to show f of x is increasing. Okay, so to show it's increasing, let's suppose a, b are in I with a less than b, and I want to show f of a is less than f of b. How am I going to do this? Well, I already told you mean value theorem. A and b are in I, and f is differentiable on I. So f is certainly differentiable on the open interval a to b and continuous on the closed interval a to b, because differentiability implies continuity, as we've discussed. So we can use the mean value theorem. By the mean value theorem, there is a c in the open interval a to b with the instantaneous rate of change at c is f of b minus f of a divided by b minus a. This instantaneous rate of change is equal to the average rate of change on the interval. Well, let's just multiply through by b minus a. Okay, so then we have that f of b minus f of a is f prime of c times b minus a. Now we are in wonderful shape because look, c is in the open interval a to b. So in particular, c is in capital I. Okay, this means f prime of c is strictly positive and a is less than b, so b minus a is strictly positive. If you take two strictly positive numbers and you multiply them together, you get a positive number. This is positive. This means that f of b is greater than f of a. And this is what we want to show. In other words, f is increasing on I. Or maybe I'll just say period. Thus. Okay? So this, I understand, this is abstract, and that's okay. But it is interesting or an important thing to understand that this, which we use all the time, and not only today, but in future chapters, okay, it really comes from the mean value theorem.